Okay, folks. The next thing I want to talk to you guys about is the pigeonhole principle. And this is kind of a cool little proof technique. So the idea is as follows. So let's say you have, I don't know, 5 boxes. Let's say you have 5 boxes. And you have 6 objects to put in those boxes. And this is called the pigeonhole principle because the usual formulation is that the boxes are pigeonholes and the objects are pigeons. But the idea is, well, if we need to put these 6 objects into 5 boxes, well, it must be the case that this last guy has to double up with somebody. So basically that's the idea. If you have more objects than boxes, then some of the object must double up in the boxes. So let's write out what this is kind of in more detail. So this is the pigeonhole principle. And it says, if a set of n bigger than or equal to 1 elements is partitioned into k sets where, well, k is less than or equal to n, then at least 1 has, oh, that's not the notation I want to use. I want to use this guy, n over k elements. And I'll explain this notation here. This is called the ceiling function. So what the ceiling function says, basically it just takes any number you like and rounds it up to the nearest integer. So rounds up to nearest integer. So that's what this is saying. So I'll just do an example or two. So if you have the ceiling of 5/3, well, 5/3 is 1 2/3, so the rounding up to the nearest integer, you get 2. And same with if you take 4/3 and round it up to the nearest integer. So that's what that means. Okay. So that's what the pigeonhole principle says. Basically, if you can think of this k, this is the number of boxes, and n is the number of objects. So if you want to put n objects into k boxes, well, at least 1 has kind of more, and this is basically saying, if you think about this, n over k is the average in each box. So this is saying that none of them it's not true that all of them have less than the average. So that's what it's saying. So that's a kind of cool way to think about it. So let's prove this. The proof is quite easy. We'll do it by contradiction. So we're going to suppose that this isn't true. So suppose each set has, let's say what? Let's say at most the ceiling of n over k minus 1 elements. Well, what happens here? Then the total number of elements is, well, let's think about it, is, let's say, is at most. So we have k boxes, and at most they have the ceiling function of n over k minus 1 elements. But if we think about this, if we take the ceiling of something, of this expression here, if we round up and subtract 1, well, then we get a smaller number than what we originally started with. So, as a little exercise to think about, you guys can think about that the ceiling of n over k minus 1 is definitely less than the original expression. And if you think about what's going on, you're just rounding up. So if you round up and subtract 1, then the original expression is going to be bigger. So we know that this is going to be less than k times the original expression, n over k, which is, of course, n. So, what does that mean? So we have less than n elements. And this is a contradiction because we want to have exactly n elements. So the theorem is true. And let's just do another example. Let's say we have let's say 4 boxes this time. And let's say $13 elements. Well, what we're saying is at least one box must have, well, what's the ceiling of 13 over 4? Well, 13 over 4 is 3 1/4, and so the ceiling of that is 4. And that makes sense because, well, let's try our best not to do that. We'll put those 3 in here, those 3 in here, those 3 in here, and those 3 in here. So we filled up the boxes as much as we can without having 4 elements in any box, but we have this element left over that has to go in one of the boxes. So no matter where we put it, we get one box having 4. So no matter what, one box has 4 or more elements, which is really cool. So this is kind of the worst case scenario in some sense. We try and spread the elements evenly, but even if we do so to try to avoid this extra element just screws it up for us. That's kind of the idea here. I will point out there is a generalized version of this. And I'll put a book reference in here. So if you look at page 288, it's there. And it basically says, well, what happens if you want different amounts in each box? So let me just give you an example of the generalized pigeonhole principle. And we'll talk about what it means after this example. So we could ask the question, how many students must be in a class to guarantee the professor gives out at least that's what I wanted. Let's say 10 A's, 25 B's, 25 C's, or 10 D's. Oh, let's put some F's in there as well. Let's erase this. Or let's say 5 F's. And so what this is saying is basically kind of fill up your boxes as much as you can without satisfying the condition, and then one more student after that will satisfy one of these conditions. So to not satisfy the condition, we need 9 A's, so to not satisfy. In the worst case scenario, we can have up to 9 A's. We can have 24 B's, 24 C's, 9 C's, 9 D's, and 4 F's. So to not satisfy this, we need, remember this is saying we want greater than or equal to 10 A's or greater than or equal to 25 B's, etc. So we want to negate that, and so we want less than 10 A's and less than 25 B's and less than 25 C's, etc., using De Morgan's law. So that's what's happening here. So this is kind of the worst case scenario. So how many students are in this worst case scenario? We add these up. So 9 plus 24 is 33. 33 plus 33 is 66. 66 plus 4 is 70. So 70 students are kind of our worst case scenario where none of these are satisfied. But if we do want to satisfy it, the next student that comes in has to come into one of these bins. They have to get one of these marks. So any more students will fill one of the bins. So 71 students, not 74. 71 students is the minimum number to fulfill the guarantee. Great. So that's the generalized version of the pigeonhole principle. I don't want to get into the technical details of it. You can read that in the book. But it's basically saying if you want to have bins of certain sizes, fill them up as much as you can without satisfying the condition, and then any extra person or object that comes in will fill will fill one of the bins, and then the condition will be satisfied. So that's what's going on here. All right, let's look at a couple of examples of the pigeonhole principle. All right, how many people must be at a party to guarantee that at least 3 people share a bits and bytes preference? And you'll remember from our last video or the video before that, we talked about how many bits and bytes preferences there are. So that's going to help us out. So we know there are 4 factorial, which is 24 different preferences. And if we think about it, that's going to be your number of bins, right? Because each person is going to go into one of these bins. So these are our bins. There are 24 bins. Okay? And each person, that's going to be our object. So the people at the party are going to be our objects. So in the notation that we talked about, the bins, 24 is going to be our K, and the people, the number of objects, will be N. And we're looking for, in fact, let me be a little clear, how many people must be at a party. Let's look for the minimum. So I'm always looking for the minimum. Was the least number of people that need to be at a party. So what do I want? So I want the smallest n such that, well, we want 3 people to share a bits and bytes preference. So that means we want 3 people in one of our bins. So by the pigeonhole principle, we want the smallest n so that n over k equals 3. So basically the easiest way to do it is figure out when n over k is a fraction, not the ceiling, but when n over k is 2, and then just add 1 to n. So we want, in the worst case scenario, we want that n over k equals 2, and then add 1 more. Because this will put all of our n people into 24 bins so that there are exactly 2 in each bin. The average number of each person in a bin is 2. But if we add one more, well, there has to be one bin that has 3 people. So let's figure this out. We know K is 24. There are 24 bins. So N over 24 equals 2. And I think you can easily see that N is 48. So 48 plus 1 is 49. And the smallest, N, is 49. So that means that if you have 49 people at a party, you are guaranteed that at least 3 people will share a Bits and Bytes preference. If you had 48, in the worst case scenario, you could have that there are 2 people exactly for each of the 24 bins. But if once you add that 49th person, they have to triple up into one of the bins. All right, let's look at another example. Oh, I don't want to do this. Okay. So, let's let A be the set of all numbers from 1 to 11. Let's show that if you pick 7 numbers, there is a pair that sums to 12. Well, the solution for this, our bins are going to be each pair of numbers that sums to 12. So our bins, or our boxes, are going to be 111, 210, 3, 9, 4, 8, 5, 7. And we have this bin 6, which we'll just have by itself. It doesn't have the same size. That's okay. So the idea is that, well, we have these bins, and we're picking 7 numbers. So our K, which is the number of bins, is 6. Our N, we're picking 7 numbers. That's 7. And the ceiling of N over K, which is, of course, 7 over 6, that's 1 1/6, so we round up to 2. So that tells us that at least one bin has 2 elements. Okay? It can't be 6 because that bin can only fit one thing, so it must be one of the other 5. That gives us our pair that sum up to 12. All right, let's look at another example. I like this one. So let's show that if you pick 5 points in the interior of a 1 by 1 square, then at least 2 points will have distance less than the square root of 2 over 2. So the distance between a pair of points is guaranteed to be less than square root 2 over 2. And this one's a fun one. So let's draw our 1 by 1 square. There it is, there. Now, this distance, square root 2 over 2, that's an important distance. If we think about it, if you draw a right angle triangle with side length 1/2 for each of the legs, then you can check the hypotenuse is going to have length square root 2 over 2. So knowing that fact, well, that tells me that, well, if I divide my 1 by 1 square, remember, I'm not allowed to pick any points on the interior. I can only pick points on the interior. I'm not allowed to pick points on the boundary. If I divide my square into 4 subsquares, and the boundaries of these subsquares, I can just define what subsquare they're in arbitrarily. So I'll say, just always go to the left and down. So I'll number these 1, 2, 3, and 4. So let's say you're right here. Then I'll say you're in square 4. If you're here, you're in square 1. It doesn't really matter. And I guess the origin, let's say the origin is in, no, let's say square 3, I guess, because that's both down and to the left. Let's keep it consistent. Okay, it doesn't really matter. But my point is as follows. Since the max distance in a square is from one diagonal to another, that's the biggest distance in a square, 2 points in a 1/2 by 1/2 square have distance less than square root 2 over 2. I know the distance from one corner to another, kind of the worst case scenario, is square root 2 over 2. You can check that again via the Pythagorean theorem. So if that's the biggest distance, then any 2 points in the square aren't going to have distance bigger than that. So we have 4 bins. Each of these squares. And 5 points. So by the Pigeonhole Principle, two of these points must lie in the same bin. So that's a cool one. I like that example. All right, let's do one more. So let's show the smallest number of integers to choose from the set. Let's start at 1, and then we'll go up to some even number, we'll call it 2n, to guarantee there are 2 consecutive numbers is n plus 1. So there's 2 things we need to show here. We need to show that it's guaranteed with n plus 1. And we also need to show that you can't do it, or you're able to avoid it, not you always can't do it, but it is avoidable or not guaranteed with any less. So n elements. Maybe I'll write elements here. Okay. So let's do the first bit. This is going to be a pigeonhole principle. So what are our bins going to be? So our bins are going to be, well, these consecutive numbers. 1, 2, 3, 4, 5, 6, all the way up to 2n minus 1, 2n. And so how many bins do we have? Well, you can see, let's look at that last number. If we divide each of these last numbers by 2, we get 1, 2, 3, all the way up to n. So we have n bins in total. Awesome. And we want to show that, well, if we have 2 elements in any one of these bins, well, they're consecutive numbers. So the smallest, I guess we already used the letter n, so the smallest, let's say m, such that the ceiling of m over n being 2 is, of course, m being n plus 1. N over n is 1. Anything bigger than n over n is going to give you a bigger number than 1, so it's going to get rounded up. So n plus 1 over n well, this is the same as, if you like, sorry, this should be the ceiling. This should be 1 plus 1 over n. That gets rounded up to 2. So, by the pigeonhole principle, we can do this with n plus 1 elements. So we show it's possible with n plus 1 elements. Now you have to show that you can avoid it. It's not guaranteed with n elements. Sorry, with n plus 1 elements, we show that it's guaranteed. We could do this with n plus 1 elements, guaranteed. That's important. Okay. Now consider the subset B of A, where B is just going to be all your even numbers. 2, 4, so we're just taking the second half of each of these. 2, 4, all the way up to 2n, so all your even numbers. Clearly, what I want to say. The size of B is n. And, well, the ceiling of n over n is, of course, 1. There's nothing to round, so you just leave it as the integer 1. So, there is a way to pick n elements with no consecutive ones. And here is that way. Remember, if we want to show something, a conditional is false, we just need a counterexample. There is our counterexample. So we showed it's not guaranteed with n, but it is guaranteed with n minus 1. So we'll say n plus 1. So n plus 1 is the minimum. And we're done with that example. Let's do just one more, and then we'll move on. This is a fun one. So let A1, A2, all the way to AN be any n integers. So we have n integers, and we gave them some sort of order. So the order we're going to use. So let's show there is some consecutive sum. Let's say there is some consecutive We're not saying how long it is, but it's just a bunch of these consecutive terms added together. So you start somewhere, say at the ith term, and you add the I plus 1th term all the way to the I plus, let's say, jth term for appropriate I and j. So we want that, well, we want I plus j, of course, to be less than or equal to n, because we only have n terms. And of course we want I to be less than n and to start at 1. So that's what makes it appropriate. So we want to show that there's some consecutive sum of some length, which has a factor of n. That's kind of a weird thing. This has to be guaranteed. All right. So, it's not clear immediately how to do the pigeonhole principle with this, but we'll see it just in a few seconds. So, let's consider the following. Let's start at A1 and go from there. So consider some first one will be A1, the second one will be A1 plus A2, the third one will be A1 plus A2 plus A3, and we'll just keep going. So we get to A1 plus A2 plus A3 plus A4 plus A5 all the way to AN. So we're looking at every possible sum starting with A1. So if one of these is divisible by n, we are done. found our consecutive sum. Excellent. Well, maybe you luck out and just one of them, A1 is already divisible by n, so you're good to go. Or maybe it's this third one, A1 plus A2 plus A3, maybe that's, by luck, divisible by n, and you're good to go. Okay, so suppose that it's not. So suppose this isn't the case. So I guess what we're doing here is we're doing a proof by cases. So here's kind of case one, is that one of these guys is already divisible by n, then we're done. Case two is that this doesn't hold. So it's everything else. Well, what does that mean? Then, actually, let me give these some labels. I'm going to call this big A1. I'm going to call this big A2. This will be big A3, all the way to big A, and I'm just defining some notation here. So rather than writing down that sum, I'm just calling it big A2 is all the numbers summed up from 1 to 2. Big AI would be all the numbers summed up from A1 to AI. Okay, then what's happening here? Well, that means that each of the AIs has a, let's write it like this, has a non-zero remainder when divided by n. Well, what does that mean? Well, that means, so each AI is, what do I want to say, is an element of one of, exactly one of, well, the equivalence class of 1 mod n, because remember, these are all the things that have remainder 1 when you divide by n, 2 mod n, all the way to n minus 1 mod n. And these are kind of our bins now. So in this case, if we don't luck out at first, these are our bins. And note that none are in the equivalence class of 0, because that means that they would already be divisible by n. But we said, in this case, they're not. So since we have n minus 1 bins, and n sequences, or sums, I guess, let's call them sums, that's our AIs, our sums, our big AIs. By the pigeonhole principle, well, we know that there must be a bin with 2 of the AIs. Because remember, we have n minus 1 bins, and we have n of these AIs, where I is just some index from 1 to n. Well, there must be a bin here that has 2 of them. There might be more than one bin that has 2 of them, but we know for sure that one bin has 2 of them. And we can even say, since well, the ceiling of n over n minus 1 is, of course, 2. All right. So, what's going on here? So, say that let's say AJ and AK are in the same equivalence class. Well, remember what it means to be in the same equivalence class mod n. So, by the definition of equivalence classes, mod n, we know that n is a factor of AJ minus AK. And let's say, without loss of generality, assume that K is the bigger one. Remember, J and K, let's be careful here. They're different elements. So we don't want J and K to be the same number. One of them is going to be bigger. Without loss of generality, let's say K is the bigger one. Okay. So let's consider AK minus AJ. So that's going to be all the numbers. A1 plus A2 all the way up to AK plus A1, minus, not plus, minus all the numbers A1 plus A2 all the way to AJ. So all of these guys are going to cancel. A1 cancels with A1, A2 cancels with A2. In here is going to be plus AJ. Since J is smaller than K, this AJ is going to be somewhere in the sequence. So that AJ is going to cancel with this AJ and all the numbers before it. And what's left is everything from J plus 1 to K. And here is our sum. This sum is divisible by n. Since we know AK minus AJ, since they're in the same equivalence class, the difference is divisible by n, and here's the difference. And it is, luckily, a sum of consecutive AIs. So we're done.